Hello, 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 Nick. How's it going? And hello to everyone else. Welcome to another day of Friendo Today. Today we're going to be doing toy problems. Hey, Nick, how you doing today, man? Okay. So, yesterday we worked on stacks. So let's work on queues today. Building 29 for queues. I'm still at bed and work started an hour ago. Hey man, taking it easy. I like it. Implementing a stack using queues, implementing a queue using stacks. That kind of seems obnoxious. First unique character in a string. Given a string S, find the first non-repeating character in it and return its index. If it does not exist, return -1. Seems like a good little starter problem. I need to go grab my big book of software engineering problems in a moment. Alright. Given a string S, find the first non-repeating character in it and return its index. If it does not exist, return -1. Okay, S equals LeetCode. So we're gonna have to look at every character. We're gonna want to count the number of characters, potentially. This is a queue problem, so I should also think in terms of how could a queue help here. So we could iterate across everything, storing the data in a hash, and then we could iterate across the hash and find the lowest value in it. Hey, Nikki. Nah, it's just a soundtrack right now. Good morning, good morning. Let's try something like that. Let's iterate across it. There's probably a much easier solution, isn't there? All right, come on, queues. How does a queue help us here? Okay. First, we're going to count the letters. 4, let I equal 0, while I is less than s dot length, I plus 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 plus. Whoa, my typing is atrocious this morning. Const scene equals an empty object. If s at I is in scene, then scene at s of I dot count plus plus. Let's iterate across them once and count them, and then just iterate across them once again and count. Okay, yeah. That works. That works really easily, actually. Else, scene at s of I equal 1. Then we should have a then for let I equal 0. I is less than s dot length, I plus plus. Let index equal -1. Const scene count equals scene at s of I if scene count equals 0, index equals I, break. Return index. Assuming I didn't mistype anything in here, which is an assumption, I think this works. Okay. Throw scene. Oh, it's not 0, it's 1. That's the issue. Let's see if this is fully correct. Nice. Well, we didn't use a Q. So mine is very slow, but very memory efficient. Interesting. As usual with coding, I have no idea what any of this means, but it's somehow very comforting to hear you work through it while I'm doing my own far less computative work. Hey, I'm glad you like it. Happy to be here to provide. I can explain this though. This is actually pretty easy to. This is pretty straightforward to explain. I can walk you through. I think I can walk a non-technical person through this. So, given a string S, so a string is just any series of characters. Characters are letters, numbers, symbols, whatever. So given a string S, find the first non-repeating character in it and return its index. Its index is a numerical representation of where it is in the string. So let's say you have a string of A, B, C. It's just A and then B and then C. The index of A is 0. Indices start at 0 generally for reasons. People didn't just pick that to make things complicated. It actually makes things less complicated, but in a more complicated. It makes things less complicated in an area where things are more complicated. If that makes sense. So I don't want to get into why arrays start at 0. They do for good reasons. Why indices start at 0. But anyway, so A would have an index of 0, B would have an index of 1, and C would have an index of 2. 0, 1, 2, 3. So there's 3 of them. So I need to take a string and tell you where the first unique letter in it is. I essentially need to take a string and tell where the first unique letter in it is. So how do we do that? So the first thing that we do here is we create a hash. And a hash is essentially something that lets you look things up really easily via key-value pairs. So you have a key, and then you have a value. So what we do is, as we go across the string, we take each letter, and we go to the hash and say, is this letter already in the hash? And that's this if statement. And this for statement here is what iterates across the loop. Iterates across the string. God damn it. This is getting complicated fast for a non-technical audience. Like, iterates. Oh, God, I need to explain what iterates is. Yada, yada, yada. All right. In short, this part counts all the individual letters. And then this part goes across the string again, looking at the counts. And the very first time it sees a letter that has a count of 1, it returns the index of that letter. And then that's the answer. I don't think that was as clear an explanation as I had hoped. I want to see what some other people's solutions look like. Okay, so here's the hash map method. That's what I did. Index of? Are those just JS functions? Cheater, 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 pumpkin eater. Cheater, cheater, pumpkin eater. Get out of here. That solution's cheating. This solution, which is my solution, much better. Okay, cool. So I kind of got that one correct. I don't quite know how a queue is a part of that one, so. Number of recent calls. You have a recent counter class, which counts the number of recent requests within a certain time frame. Implement the recent counter class. This has a lot of downvotes. Let's read it. Maybe we might not do this one though. You have a recent counter class which counts the number of recent requests within a certain time frame. Implement the recent counter class. Recent counter initializes the counter with 0 recent requests. Int ping I adds a new request at time t, where t represents some time in milliseconds and returns the number of requests that have happened in the past. Okay. We need to return a filter. Okay. Let's try this one out. I don't quite get why this one has so many downvotes, but let's try it out. This dot requests equals an empty array. Do we need anything besides requests? I don't think so. Ping. This dot requests dot push t. So you push the time of the request into the requests array. Return request is greater than t minus 3000. Let's try that. I think I have to do greater than or equal to. There we go. This is really really easy. Why do people have a problem with this? What do you mean this question doesn't make any sense? Well, it made sense to me. I don't know what to tell you. All right, wow, we've really knocked 2 easy ones right out of the park. Really nice. Let me go grab my engineering book. The next topic is trees and graphs, which are a lot more complicated. I'm gonna give my brain we've already done 2 problems, and I can already feel my brain kind of starting to heat up. I'm gonna give it a very brief break while we browse some stuff. New feature, study plan. Detailed explanation of graphs. $35 a month for LeetCode. Damn, that is pretty expensive. Let's start some tree problems. Oh boy, these are gonna be tough. I'm honestly gonna have to just read solutions for the beginning of it, probably. Binary tree in order traversal. All right. Let's see if we can reason our way to a solution on this. It has been like 5 years since I've done trees. Not 5 years, what the hell am I talking about? Like 4 years, 3.5, something like that. Okay, so what are trees? First of all, I'll explain what they are just so there's at least a little bit of context for non-technical viewers. A tree is a data structure characterized by parent nodes that can have multiple child nodes. And they kind of look like trees, like evergreen trees, which is why they're called trees. Well, actually, I don't know why they're called trees in that regard, but they do kind of look like trees. I guess it's because they have branches, really. It's because they just have lots of branches. So this is a binary tree, which means each node will only ever have a left and a right branch. Return the in-order traversal of its nodes' values. that'd be 1, 2, 3. Two comes before 1. Output 1, 3, 2. I don't quite get why 3 is coming before 2 though. Confused by what it means by in order traversal. All right. Yeah, so you need a stack for it. I just need to learn more about what they mean by these concepts. I don't know what in-order, pre-order, and post-order traversals mean. Unlike linear data structures, array, linked list, queues, stacks, etc., which only have one logical way to traverse them, trees can be traversed in different ways. Following are the generally used ways for traversing trees. Depth first traversal. In order. Left, root, right. Oh, so that literally just means left, root, right. So you go left, left, record. Up 1, middle, right. Up 1, middle, right. Okay. I get it. All right, in order. I get what in order traversal is. Okay. So you depth first. It's depth first traversal. You go as deep as you can. Okay. Cool. Hell yeah. All right. In order, pre-order, post-order. I should learn how to do these both in terms of recursion and with stacks and queues. Okay. So we know we need to use a stack. And now we know what that means. Okay, so 1 doesn't have anything, null, boom, comes here, boom. Yep, all right, I know this is 1, 3, 2. All right, cool. In order traversal makes sense. So, how do we actually traverse? Okay. While there's a root and a stack dot length. If there's root, stack dot push root, root equals root dot left. So you're pushing the roots onto the stack. Else, root equals stack dot pop. There we go. Else root equals stack dot pop. Okay. There we go. That. All right. I need to run to the restroom, but yeah, I dig this. Okay. Okay, I think I've looked at this enough. Let's try and implement it. Okay, so we are doing depth first traversal, which means we are going down. Okay. While there is a root, stack.length, if root else, so if we have a root, stack dot push if there's a root. Stack dot push root. We push the root on, and then root equals root dot left, and then we traverse to the left. So if there's a root, we grab it, traverse to the left. Else root equals stack dot pop. Res.push root.val. Okay, let's test this out with some of these test cases. Okay, so root comes in, it's this. While root, okay, root, stack.push the root equals root.left, which is null. So this is now null. Else root equals stack.pop. Boom. That's that stack, which is the 1. Res.push, root.da. Now the new root is this root, which does have a root. I don't know if we want to do this sort of reassignment. This seems a little sloppy, but whatever. Out of memory. All right, I must have set an infinite loop or something. Oh, whoops. I didn't do pop correctly. Duh. Very nice. Okay. So, stack for depth first traversal. Let's try and do this. Let's try and do this via recursion now to practice some recursion. Recursion should be easier, theoretically. All right. If there's a root.left. Busting my brain. Function in order traversal node if left node. So you're taking the table, passing it down. You do depth first search down the left. Oh, I already did this one. Wait. All right, we are at 1 hour. Same tree, symmetric tree. Given the roots of two binary trees, P and Q, write a function to check to see if they are the same or not. They're considered the same if they are structurally identical and the nodes have the same value. Okay, I guess we want to do 2 tree traversals and then compare the results of the tree traversals. But can you do it during the tree traversal? I think you can. Wait, can you? It does get kind of messy, doesn't it? Okay, so we could traverse both trees, convert them into arrays, and compare the arrays. But could we compare them directly as trees without having to convert them to arrays first? Okay, let's see if we can do this while we're traversing. Const p stack equals that. Const q stack equals that. While p or q or p stack dot length or q stack dot length. is same. If p dot left and q dot left no, it's if p and q p equals p dot left, q equals q dot left, p stack dot push p dot val, actually not the val, push p onto it actually. Q stack dot push q else if else There we go. Then again, if this doesn't work, that would still be the case. If there's no P or there's no Q, we break. If we pull this out, we get a runtime error. Is this not breaking the loop? someone I don't want to pick up for. Who cares? No P or there's no Q. The same equals false. Break. I'm really perplexed here why this is not working. Because we're hitting this, and we're setting it to false, and we're breaking the loop. So the next thing we do .59 of 60 test cases passed. I'm only failing on one test case. Wish I'd get. Gosh, what the hell? It doesn't even error out. Why is this output true? is really weird. This, to me, seems like it should be working. But it isn't. And I'm really perplexed by that. Passing all the test cases except for one. Wrong here. All right, let's go to the solutions. Okay, this is a recursive solution. All these people doing recursion. Wow, everyone's doing recursion. Maybe that's the route I should have taken. I'm just feeling a little rusty and afraid of recursion currently. Alright, I gotta get some breakfast. I'm hungry. I haven't eaten yet. I'm gonna get some of that started, and we'll take a break. Microwaving some oatmeal. This is really weird. This should be working, as far as I can tell. right. All right, we got about an hour and a half of toy problems under the belt. My brain is definitely feeling the work at this point. We'll take a break. We'll look at this just to get some practice in while we're waiting.
Welcome to another tutorial on Geeks. Hello friends and welcome to another tutorial on Geeks for Geeks. In this tutorial, we are going to cover the tree traversal techniques. In simple word, traversing a tree means to read or process the content of a tree node exactly once in some order. Now since tree is not a linear data structure like an array or a linked list where we have a logical start and a logical end, therefore it can be traversed in many ways. We broadly classify traversing into two ways: the breadth first traversal and the depth first traversal. These techniques are general way of traversing a graph, and since tree is a special form of graph, we can use them. Now breadth first traversal is also known as level order traversal in trees. Depth first has further categories. It can be pre-order traversal, in-order traversal, or a post-order traversal. We'll go through each of them one by one. First, let's have a look at breadth first traversal. In trees, we also call it as level order traversal. We have done a separate video on level order traversal, which is quite in depth and you can refer to it. For now, understand it as follows. Level order traversal refers to traversing the tree nodes in a level by level fashion. Let's see it with an example. In this tree, if we start from node A, the order of traversal would be: first we visit this layer,
I got
then
spam.
layer 2, then this layer, and finally the last layer 4. So our final order will look like this. Now we look into the depth first traversal. We divide it into three categories. First is the pre-order traversal. In this, we first traverse the root, then left sub.
Lighter. Oh my goodness. More bathrooms, sorry. All right. Where'd the music go? Do the recursive traversal. Okay. Let's see if this works. Probably not, but it's the first time. We get a root of 1. It has no root dot left. So, but it does have a root dot right. So we call this on the root dot right. This has a root dot left. So we call this on the root dot left. Then we push in that doesn't work. There is no root dot left. We push that value in, we check to see if there's a root dot right. There is a root dot right. We're back in here, there is a root dot left. We dive down to the root dot left. There is no root dot left. We push the value in, there is no root dot right. We return the nodes. Nodes return, nodes return. Okay, cool. I think this might work. Nope. We didn't get the 2. You don't want to return, you just want to build it out. There we go. All right, we got this one. Nice. All right. We are just about at 2 hours. I think we'll call it a stream for right now. But I will be back this afternoon with some more work. Until then, I hope everyone has an excellent morning. And I will see y'all this afternoon. Happy to share in the vibes, Nikki. Thanks for